Welcome to The Kingstonian, a podcast that profiles people who are passionate about what they do for a living, what organization they belong to, or the community they are a part of. Here is your host, Dave Cunningham.
Thank you, Steve. Hello, everyone, and welcome. In this episode, we dive into the fascinating world of physics with someone who knows it inside and out. If you haven't thought about physics since high school, don't worry. It's still shaping the world around us in ways you might not even realize. My guest is Dr. Art McDonald, a professor of astrophysics at Queen's University in Kingston and a true expert in his field. A decade ago, he was awarded the Nobel Prize in Physics for his groundbreaking work on neutrinos, mysterious particles that help us understand the universe. We'll break down what they are, why they matter, and how his research took him 2 kilometers underground into a nickel mine in Sudbury. Get ready to explore the wonders of physics in a whole new way. This episode was recorded in mid-March 2025. Art, welcome to the program, and thank you very much for your time today.
Well, it's a pleasure. Nice to do this.
Before we get started, a bit of a fun question. I would like you to weigh in on the debate that's been going on for 300 or 400 years concerning one of the world's best-known physicists, and he was a whole bunch more than just that. But we're talking about Sir Isaac Newton and whether or not the apple did fall on his head or not.
Well, I don't know whether it fell on his head. It fell on his thinking processes.
Mm-hmm.
That's for sure. And what was revolutionary, and I'm taking great liberties with the details of what he dealt with, because he made contributions in many remarkable ways. But what he realized that was revolutionary in its nature was that the force of gravity between the Earth and any object, that which holds us to the Earth or causes an apple to drop from a tree, is the same force that has the moon in orbit around the Earth.
Mm-hmm.
And he took that information about the tree and the apple and combined it with astronomical information about the moon, for example, and came up with a law of gravity that was quite remarkable in its day. And so it's that sort of approach to the world around you that makes a really good scientist. You really need to keep your eyes open and attempt to understand the things you see, and you'll learn something from it.
And be able to communicate that to other people as well.
Absolutely.
Okay, let's talk about physics. The role you have played in changing the thinking about a certain aspect of astrophysics and how that research impacts those outside the scientific community. But let's go back to Sydney, Nova Scotia, and how you became interested in studying physics.
Well, in Sydney, Nova Scotia, I actually became interested in studying math. I had a really good mathematics teacher in high school, and very often people who do well in society will mention the fact that they had a good teacher that inspired them to learning. In our case, this fellow's name was Bob Chafe, and I say our case because in a class of 35 students, there are 3 PhDs, 2 in mathematics and 1 in physics, and several others who have done master's degrees in science and so on. Mm-hmm. Quite a remarkable set of extra classes that he would run for us to really get us inspired in mathematics. So I went to university with the feeling that I really liked mathematics, but I didn't want to study it for its own sake. I wanted to figure out how it could be best applied in science. Physics turned out to be that venue, and to me, it was quite remarkable what I learned in my first year physics in university, which was far above the quality of what I had learned in high school, and also, again, taught by a great physicist, Ernie Guptill of Dalhousie. I suddenly realized that you could apply mathematics to really understand what's happening around you. Mm-hmm. First year, of course, in very simple terms. But eventually, as it carried on, I became fascinated by the breadth of ways in which mathematics can help us to understand our world, and ended up doing experimental physics for a master's degree before moving on to Caltech in Pasadena, where I did a PhD.
Now, as you were studying physics, was there any particular historical figure that you gravitated to or thought about or inspired you in your study?
Perhaps not so much historical figures, but at Caltech, I really had quite an array of professors who, in fact, had Nobel Prizes in a range of subjects. Richard Feynman taught quantum mechanics, and he's a legendary physicist of the 1950s and 60s. I was at Caltech, of course, between 65 and 69. The head of the laboratory where I ended up doing my research was William or Willie Fowler, who worked out all of the nuclear reactions that power the stars like the sun and the whole sequence of development of how the elements are created in a series of reactions in the stars, which he also received a Nobel Prize for a few years after I left. That activity was going on, and ironically, so were the preparations for the first measurements of neutrino particles from the sun, which is what we eventually sorted out as to the fact that it meant that the measurements that were made meant that neutrinos had properties that previously were unknown. So rather than historical figures, I had professors who were inspirational on their own. And but then later I became a professor at Princeton in the 1980s, and actually, I was just back there last week for a retirement of one of my colleagues when I was there, and so we went to dinner, and there were five Nobel Prize winners in the room,
Really?
all of whom had been colleagues when I was at Princeton. Well, in those two locations, Caltech and Princeton, there was quite an inspirational group of people that I was working with. That more than the historic figures, but if I had to pick one, I'd pick Einstein for that case.
I was going to come back to the business of important teachers later on in our conversation, but since we've sort of talked about it here for a couple of minutes, underscore the importance of the people who go into teaching and inspire their students to study harder and explore the things that really inspire them. So teachers are very important in this whole equation.
That's very true. And you tend to think of teachers, that's what the public is mostly knowledgeable about, is teachers in elementary, high school, and even university. But there's another group of teachers, and that's perhaps why I've spent more of my time. I did teach undergraduate students through my days in Princeton from 82 to 89, and then at Queens between 89 and when I retired from that form of undergraduate teaching in 2013. And I'm hoping that I inspired those students. But then there's a group of graduate students that I worked with in terms of mentoring them to learn how to do experimental physics. And I'm still doing that. I'm still interacting with the group here, several groups here that are working on large experiments internationally. And whereas I'm not the direct supervisor anymore of such students, I really enjoy still working with them and can sometimes inject into the conversation things that are the essence of how you do experimental physics and things you have to think about in order to be sure that you've convinced yourself and thereby others that what you've measured is accurate.
Yeah.
Or the uncertainties and so on. And so teaching at all levels, all the way from kindergarten, granddaughters. I have 9 grandchildren, 8 of whom are girls. The youngest is 6. And so I'm very interested in what she's learning in grade 1. And it's wonderful at that age. I mean, you see the sponge action happening as they pick up so many things. And the quality of the teacher she has right now, for example, happens to be in Oakville.
Mm-hmm.
They really have made her feel comfortable in her new school there this year. It's just a quality of personality of the people who take teaching as a vocation that is very inspirational. All the way from that to one of my closest colleagues here at Queens wins awards from the students for being the best teacher in first year engineering at Queens. And this is Tony Noble, the director of the institute that he created, and they ended up naming after me here. that because of the Nobel Prize, but he's just a fantastic teacher and he loves what he's doing. And the students love him too.
Now, before you went into teaching, after you did graduate and got your doctorate from California, you spent 13 years working in Chalk River
Right.
at the Atomic Energy of Canada Limited plant there. What was the purpose in going there? What were you doing there?
Well, in those days, and in fact, it was an echo of what originally happened at Chalk River. Chalk River, you should understand, was created at the time of the Manhattan Project, later opened in 1945. It was a place where British and others who could contribute to the Manhattan Project, particularly if you like, all of the physics of what they call splitting the atom. That's the general term that's used. Fission of heavy atoms like uranium and plutonium. It was developed as a place outside of the United States where these people who were not able to work at Los Alamos came together and made significant contributions. And from the very beginning, Chalk River was mainly interested in developing power reactors and peaceful uses of atomic energy. Their efforts in building bombs and so on finished when they were attempting to support the Manhattan Project. So at the time, they were hiring pure physicists, people who were interested in understanding the physics of the nucleus and what goes on there. It was very fundamental what they were trying to do before they started applying those activities. And that continued on into the 80s and 90s. I was there during the 1970s, actually, and we had an accelerator laboratory that enabled me to spend essentially full time studying various elements of nuclear physics in great detail. And so Chalk River at that time had a significant basic science component occurring, and I benefited greatly from that because for about a dozen years I was able to pursue research, well supported. The accelerator laboratory was well supported and doing very basic things. And we were doing things like testing the standard model for elementary particle physics, but in nuclei, as opposed to at the highest energy accelerators. And we made significant contributions in that area. Ironically, one of the things we did with the Sudbury Neutrino Observatory was to observe the first discrepancy in the standard model of elementary particle physics. And so first proving some things right and then finding some things that were wrong. And in most cases, using the nucleus as a laboratory to do that. And that started at Chalk River.
Now, the major field of endeavor that you've pursued over the years was the study of neutrinos. And for those of us who haven't taken a physics course in a long time, can you explain what a neutrino is?
So we think there are three basic building blocks of nature right now. We think. Scientists are always very careful to say, as far as we know today, this is the case because, in Einstein's day and beginning of the 20th century, this was not the picture at all, and it's all developed since then. But electrons, quarks, which are inside the nucleus of an atom, by being inside the neutrons and protons that are inside the nucleus of an atom. Electrons, which we know well, they run in our wires. Quarks, central part of the nucleus of an atom. And the third particle is a so-called neutrino. And it's a very unusual particle, which surprised people very much when it first was postulated to exist. And then after 20 years or so, finally observed, is a particle that occurs in very rare radioactivity when one quark turns into another quark and it emits an electron and a neutrino. Those particles only interact through what's called the weak interaction, the weakest of all the forces we know. We have a weak force, a strong force. Strong force holds the nucleus together, binds all those quarks and protons together. And finally, the electromagnetic force is what runs our world. That's electricity, it's magnetism, it's the way in which we power our lives, basically. It also influences all the chemistry that goes on. Neutrinos don't participate in either the electromagnetic force or the strong force, only this weakest force that's involved in that radioactivity I referred to. And so they're essentially out of our normal experience. And neutrinos are produced in enormous numbers in the nuclear reactions that power the sun. And so right now, we're bathed in neutrinos, but only once in our lifetime would one of these neutrinos stop in our body and change one atom. So we're basically oblivious to them. But right now, if you look at your thumbnail, there's 5 million neutrinos just went through that thumbnail the last second from the sun.
Yeah.
So in order to detect those, we had to build a detector the size of a 10-story building containing $300 million worth of very precious heavy water, which I'll describe in a minute, and make it ultra clean. In particular, the reason why we needed it ultra clean was to avoid any other signals from local radioactivity 2 kilometers underground. We were shielding out all of the cosmic rays that otherwise give you the northern lights, or things like them give you the northern lights. But it's clear that this is the lowest radioactivity location ever created, and we had to do that to make these measurements. And that's because neutrinos are extremely difficult to detect. And so our detector, the size of a 10-story building, still only observed 1 neutrino an hour from the sun. So we had to count for a number of years in order to really determine what was happening. And what we did was measure directly the fact that the number of neutrinos coming from the sun is less than is calculated by calculations that otherwise predict how the sun burns. And the reason it turns out that there were fewer of the type of neutrinos emitted is because they changed into other types of neutrinos that were undetectable as they traveled from the sun to the Earth. And that is outside the standard model of physics. And of course, as you started in this question, well outside everybody's experience.
Let me stop you there for half a second. Now, we talked about the fact that these neutrinos are really hard to detect. And they don't show up in a lot of other things that we're accustomed to feeling and hearing about with respect to electrons and magnetism and that sort of thing. Why study them to start with?
Well, first of all, it's really an existential question, or part of a big existential question. Existential questions typically are questions about how life and human experience developed over the years. This is a question of how everything developed. How did we end up with the world that we see around us as it is? There's a theory that has now become very well accepted to the degree that, in fact, another Canadian, Jim Peebles from Manitoba, who was one of my colleagues when I was at Princeton in the 1980s, he developed a theory which starts with the Big Bang, 13.6 billion years ago, and extends to the present day and works quite well. There's still some questions to be answered, to be sure, but works quite well as to how all of the matter that we're made of was formed during that period of time, and some large fraction of it was actually formed in stars like the sun. And our measurements also verified, once you put in this information that neutrinos can change from one type to another, that verifies the calculations of the sun very well, and those calculations are the same ones that are used to calculate how you do fusion power here on Earth. Fusion power being attempting to capture the sun in a magnetic bottle, typically. So from that point of view, our measurements were valuable from a human perspective of a source of power that once developed, and it's been worked on for a long while, but they're getting closer every day, will be almost inexhaustible and clean. And so from that point of view, we have a practical outcome. But our objective was not so much to do that as much as it was to contribute to the overall understanding of the laws of physics right down to their basic level, and to contribute in several ways to processes that occur that influence how the universe has formed. Neutrinos, it turns out, are significant in several elements of how the universe has formed, and we were studying their properties, and that fits into these models in ways, as it turns out, are necessary in order for the universe to form in the Big Bang theory in the way that Jim Peebles has worked out. So we're doing existential questions, understanding physics at its very basic, and at the same time, in various ways, contributing to valuable technology here on Earth. The other ways being developments we make in order to accomplish our frontier experiments.
Now, you had spoken about how you were engaged in the experiments and describing the facilities that you had created, and you're talking about the Sudbury Neutrino Observatory. that came together back in 1984, as I read somewhere, and various international scientists got together to form this particular observatory. Now, you had said that it's 2 kilometers deep. It's a mine shaft, right? That's 2 kilometers deep.
It's a level of a mine, 2 kilometers down, still a very active nickel mine, Creighton number 9 nickel copper mine near Sudbury, owned by Vale Company now. It was Inco when we were starting the project. And they very nicely allow us to have an experimental area at what they call the 6,800-foot level of the mine. They're actually mining still down at the 8,000-foot level and taking thousands of tons of ore out of the mine every day. At the time we excavated the cavity, as I said, the size of a 10-story building, at the level where we are, this was groundbreaking is too much of a of an oxymoron in this case. This was quite an innovation to build something that big. And that was a value to them in terms of pushing on with the ability to do excavation at even deeper and more stressful points in the mine. And so basically, by doing this, we were testing very basic theory of mining engineering and had experts from Queens, Toronto, Laurentian involved in the work that we did. So as I say, there are various things that you do in basic science that push the frontiers of technology. Yeah. But yes, it's eventually created the lowest radioactivity location in the world for the original SNO, or Sudbury Neutrino Observatory. And it went so well that the government, in looking for new laboratories to engage Canadians with international scientists to come and work here, that they expanded the laboratory at that 6,800-foot level by a factor of 3 in excavation and created spaces that are now occupied by 5 or 6 other international collaborative experiments taking advantage of the low radioactivity environment.
When you talk about making the area clean for you to do the experiments, when you use the word clean, how do you define clean?
Cleaner than a hospital operating room, similar to the sorts of rooms that are created in buildings to fabricate computer chips to keep dust and radioactivity out of, in our case, mostly radioactivity out of our detectors. So it's class 2000 is the official term. That's a measure of the number of particles of dust that there are in the air in a cubic meter that are greater than a half a micron or so in size. And then in the experiment, in the areas where material might actually get into the detector, we're able to put further layers that get us down to 100. So if you think on a summer day, if you're sitting indoors and looking at a sunbeam coming through the window, even today, you could see that. You might see dust in that sunbeam.
Mm-hmm. Yeah, yeah.
You would not see a single one of those if a sunbeam could get down 2,000 kilometers into our laboratory.
Well, that's what I'm having a hard time imagining is a really clean area, 6,800 feet down in a mine shaft, and how you make that clean. Which is interesting.
Well, first of all, like all clean rooms, everyone dresses for the occasion. People who come down underground and walk for 1.5 kilometers in mine clothing, take off that clothing, have a shower, and put on clean, lint-free clothing similar to what you'd wear in a clean room on the surface. But in addition, we have enormous air filters that create 10,000 times lower levels of dust than you have in the exterior mine. So every bit of air that comes in runs through one of these filters, HEPA filters as they're called. And and this process goes on continually to keep the area dust-free.
Getting back to the experiments that you started doing in this location where you were involving heavy water to help you figure out what was going on with these neutrinos and the fact that they had changed on their way from the sun to where you were trapping the odd neutrino to look at. The business of heavy water, for those people who may not understand what that is, can you briefly describe what heavy water is?
Yes. So in every glass of water you drink, there are roughly 1 in 6,000 of the molecules of H2O that are actually D2O, deuterium oxide. Deuterium is a type of hydrogen where there's an extra neutron in the nucleus of the atom along with the proton, which is what's in hydrogen. H, the hydrogen atom itself, is a proton in the middle surrounded by an electron. That H is what goes into the molecule H2O. D2O is a proton and a neutron in the nucleus, surrounded again by a single electron, because its negative charge is matched by the single positive charge of the proton, and that neutron is neutral. That means you have a molecule that's almost identical to the H in the H2O, except it's a bit heavier, 10% heavier. Now, that extra neutron, on the other hand, can be very valuable. It's valuable in CANDU style nuclear reactors because what they require is to slow down neutrons after the neutrons are produced originally by the fission of uranium. The uranium atom splits apart, or nucleus splits apart, and produces two lighter materials and a number of neutrons. And in order to maintain a controlled nuclear reaction in the reactor, what you want is to slow down those neutrons so that when they bang into another uranium nucleus, they induce it to do the same thing and produce even more neutrons. And that's the way in which the fire burns, if you like. Mm-hmm. So in the Canadian nuclear reactor, you could use hydrogen to do that, but hydrogen really likes to grab the extra neutron and make deuterium. But if you've already got the neutron in there in the form of deuterium, if you like, there's a much harder process to grab another neutron and take it out of the stream. Instead, it just bounces off typically and slows down the way we want it to. And that was great for Canadian nuclear reactors. And so when we wanted to borrow some of this heavy water, we were able to do so for 10 years or so to do our experiment. In our experiment, it is that extra neutron that enabled us, with the availability of heavy water, to make a unique measurement that told us that the type of neutrinos coming from the sun or produced in the nuclear reactions in the sun were changing into other types before they reached the Earth. And that was the fundamental thing. That means that neutrinos have a mass greater than zero, and it also describes other processes that happen in stars and in supernova, where some of the elements are made, that are quite unique, which contributes to the Big Bang theory.
Now, when I was preparing for this conversation, I was reading about this whole process, and I understood the fact that you were examining these neutrinos and that there were three distinct types of neutrinos. And there was never any discussion about the other two. Like, one is the electron neutrino, and then you have, I'm not sure how it's pronounced, tau and muon.
Tau and muon.
Muon. Are those of any concern or of any interest, or is it just the electron neutrino that you're focused on?
So electron neutrinos are the type of neutrinos that are associated with the radioactive decays I mentioned, which is what's happening in the sun and these nuclear reactions powering the sun, fusion reactions of, interestingly, deuterium, deuterons, same thing that's in heavy water, and other light nuclei, and the start of the buildup of the whole sequence of the periodic table, which starts in stars like the sun. The muon and tau neutrinos are really only observed in much higher energy processes, first identified in cosmic rays and more commonly now produced in high energy accelerators. But it turns out that the particles, muons and taus, only get produced at these much higher energies. The neutrinos associated with them still have really tiny mass, and therefore the processes that go on that convert electron neutrinos into these other types happen in a quantum mechanical but straightforward way. And therefore we're only interested in them in the sense that they tell us that that's what happens with electron neutrinos, rather than we're going to use them in some effective way on Earth.
Now, the fact that you were able to prove that neutrinos do have mass was what enabled you to be awarded the Nobel Prize for Physics back in 2015.
That's right.
along with your co-recipient. Now, were you working with Dr. Kajita, or is he doing something similar?
He actually, well, we both were leaders of large projects, and there's 200 or more people that really did the work on the Sudbury Neutrino Observatory project, and I'm very conscious of the fact that I received a Nobel Prize, and it was a recognition for everybody.
Mhm.
In fact, we had made a success, and so I simply try to represent them well. Kajita does the same thing in terms of
Mhm.
his large collaboration in Japan. They were studying neutrinos that are produced in the atmosphere by cosmic rays that bombard our atmosphere. And as I say, one component of them actually produces the northern lights. So you have a feeling of how substantial they are. They produce muon neutrinos, and they observed the muon neutrinos changing their type as they traversed the Earth. We were studying electron neutrinos produced in the sun, and therefore the prize was awarded for two separate observations. In one case, for the disappearance of muon neutrinos in their measurements, and in our case, both the observation of the disappearance of electron neutrinos, but also the observation of effects due to the other two types, which told clearly that it was a transformation and not just some suppression of the neutrinos. So we added something concrete to the mix, but also we're studying the other neutrino types.
Now, how does a research scientist like yourself react when they get a phone call at 5 o'clock in the morning
Well,
from Sweden saying you've been awarded the Nobel Prize?
the first thing you do is pick up the extension and hear a Swedish accent and say to your wife, "No, no, 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 don't yell at them for calling at that time in the morning." She was
It isn't a robocall.
not a robocall. At that point, I was speaking to the members of the committee, starting with the chairman, and they in turn congratulated me and explained, that we were sharing the prize with the Japanese collaborators and so on. And then the final fellow who came on the call was the secretary of the committee, the permanent secretary, at least for a number of years, and Lars Bergstrom, and I knew him because he's a neutrino physicist in Stockholm, and I had visited Stockholm a number of times. The Nobel Committee actually holds mini conferences on topics that they are considering. And so I had seen him in that context and also in some other lectures I had given there. And he knew that I was a hockey fan, particularly a Leafs fan. He is similarly a hockey fan. He comes from Peter Forsberg's hometown and so on. So he congratulated me and then said, last time we talked, we were talking about hockey as well as physics." And I said, "Yeah, I just watched the last Leafs game and I wish Matt Sundin had not retired. They could really use some help." This was 2015, before the Austin Matthews area and period, etc. Anyway, so I was asked, I think, by the Whig Standard at the time, why do you think he was, bringing this up at this point? And I said, well, in the past there have been hoaxes, and so situation he was trying to create was a little bit of, personal interaction, so it was clear this wasn't a hoax.
Yeah.
And so the headline in the Whig the next day was "Not a Hoax." Nothing to do with the Nobel Prize in the title,
Yeah.
just not a hoax. And then there was an online blog that stated that it was typically Canadian to discover that you won a Nobel Prize and all you wanted to talk about was hockey. And in addition to that, this was actually a wonderful opportunity to me when I went to Stockholm to meet Matt Sundin and Boya Salming and so on. And in Matt's recent autobiography, he cites the occasion when I mentioned him in the same sentence as saying thank you for having received a Nobel Prize as being a prototypical Leafs Nation person. So, and also the ceremonies that took place in Stockholm, where he and Borja were included, the Canadian embassy. In any case, but then I turned to my wife and said, "What do you think this means?" And it has meant something very different in our lives.
I had the opportunity to go online and watch a lot of the ceremonies and videos that the Nobel Committee puts up, and I was impressed with the fact that there was this banquet that took place. Now, I don't know when. I gather this would be after the actual presentation ceremonies, and there looked to be an awful lot of people sitting down for dinner.
The ceremonies take a week altogether, and the city of Stockholm really turns out for these different ceremonies. But the people at dinner, there are 1,500, and they are by invitation only. You are only allowed as a prize winner to invite 7 people. But I learned from a previous prize winner from a large collaboration that you can, by having people agree to share whether they go to the concert or the reception at the museum or whatever, you can get tickets for more than the 7. And there's actually a subsidiary location where they have more people seated with closed circuit TV, same meal, same plates and everything.
Yeah.
And so I managed to get 35 people, which for me was important to recognize, because what I did was invite a number of collaborators from the experiment, and in all cases where they had spouses, the spouses were invited as well, because the spouses in all cases are a remarkable contributor to the success of a all-encompassing project like this. And so we had a real party. Everybody stayed at the Grand Hotel. Everybody got fitted out in tuxedos. The Nobel Committee is very good about making it possible for everybody to participate. So, including the principal of Queen's, of course, Daniel Wolfe at the time.
So that was 10 years ago.
Yes.
What sorts of things are you working on now? Are you still looking to get answers to questions you still have?
Yeah, I mean, it always has been the case in science, and that's why scientists will say, we only really think we know, quotation marks on that word know, things that we have measured with great accuracy, because we've had so many surprises, which over the years, going back to Newton, that was a surprise that the apple and the moon were related. Well, our observations on neutrinos were a similar surprise, but perhaps less understood by the general public.
When I was doing a bit of research, I was watching those videos from the Nobel presentation ceremonies and the banquet that followed, and you delivered a short little speech. And I think a couple of lines from that speech would be a good way to wrap up our conversation. And these are your words: behind every success, there is effort. Behind the effort, there is passion. Behind the passion, there are people with the courage to try. Art, thanks for trying.
Thank you. And those are the people I like to pay tribute to, my colleagues.
Thanks for your time today, and all the best.
Thank you. And to you.
Dr. Art McDonald, physics professor at Queen's University, and in 2015, co-recipient of the Nobel Prize in Physics. To those of you who have taken the time to listen, thank you. I'll be back soon with another conversation.
The theme music for the podcast is Stasis Oasis, written and performed by Kingston musician Tim Aylesworth. If you have any questions, comments, or suggestions about any of the episodes, please send a note to thekingstonianpodcast at gmail.com. For details on upcoming guests, follow us on Facebook. The Kingstonian Podcast is hosted by Dave Cunningham and produced in Kingston, Ontario, Canada.